Chapter 7. Shear stress in beams or flexural shear stress. That is shear force with bending. A simply supported beam at a cross section xx. Cross section at the rate of xx. This is neutral axis. EF total depth d, width b, v. Secondary parabolic. This is shear stress distribution. We will discuss that later. Assumptions: material should be isotropic, homogeneous, and should follow Hooke's law. Due to shear force, versus shear stress, due to shear force variation, sh- shear force V, shear stress will not change across width. The cross section constant from E to F. Shear stress will only change along depth of cross section. Y along depth of cross section y. At any level CF, the shear stress is given by tau is equal to VA y bar by INA B. Tau is equal to shear stress at level EF. V is equal to shear force at that cross section. INA is equal to moment of total cross section about neutral axis. B is equal to width of level EF. A is equal to area either above or below the level EF. Y bar is equal to centroidal distance of considered area from neutral axis. A y bar is equal to sigma AI YA is equal to integral y dA. EF A above EF y bar is equal to centroid of considered distance from neutral axis. Due to shear force V, the shear stress will be produced on two mutually perpendicular planes. One vertical plane parallel to shear plane, second horizontal or longitudinal plane perpendicular to shear force. Okay, if V is like this, then tau will be like this, and another perpendicular horizontal tau will be like this. Due to shear force V, the variation of shear stress across depth of cross section will always be parabolic with zero value at top and bottom and maximum somewhere in the middle, not necessarily at neutral axis. Average shear stress. Tau average is equal to shear force by cross sectional area. Tau average is equal to V by BD. Shear force without bending used in machine design. BD tau average. But here, if there is V, then there will be bending in real cases. Shear stress distribution in various cross sections. First, rectangular cross section. DB neutral axis EFY V. Secondary, tau is equal to VA y bar by INA B is equal to V into D by 2 minus Y into B into Y plus half into D by 2 minus Y by BD cube by 12 into B. 6V by BD cube into D by 2 whole square minus Y square. This is the distribution which is secondary. Tau max at Y is equal to 0 is equal to finally 6V by BD cube into D square by 4 is equal to 3 by 2 V by BD. Tau max by tau average is equal to 3 by 2. Not only in rectangular cross section, but a cross section which is made of rectangles like IE, T, etc. We will also have maximum shear stress at neutral axis itself. Okay, if you use rectangles also, neutral axis at neutral axis only, we will have maximum shear stress. For a rectangular cross section, find out distance from neutral axis where the average and actual shear stress becomes equal. Actual shear stress at any distance y. Tau is equal to 6V by BD cube into D by 2 whole square minus Y square. Is equal to 6 by 4 minus 6Y square by 2 is equal to 1 half is equal to half is equal to 6Y square by D square by 12 is equal to Y square, Y is equal to D by root 12. For a rectangular cross section, find out shear force resisted, which is resisted by appear 1/3 portion by applied shear force V. So d by 3 upward portion is upper 1/3 portion d by 3 y dy integral distance here from d by 6 to d by 2. variation, we have to write 6v by bd cube into d square by 4 minus y square into b dy. D square, finally substituting those terms, we will get 7 by 27 d cube after solving. 7v by 27 d cube. These are workbook questions which are general questions. Tau is going to VA y bar by INA. In case of beams, the magnitude of maximum bending stress, which is much more than the maximum shear stress. Therefore, design of beam should always be done on basis of maximum shear stress. And circular cross section. A circular cross section IN YE EY dA is equal to EF dy. EF is equal to 2 root of r square minus y square. INA is equal to pi by 64 d power 4 is equal to pi by 4 r power 4. A y bar is equal to integral y dA is equal to integral y is equal to y to r. This we are finding only for this section. Y to r by 2 y 2 root of y r square minus y square dy. A y bar is equal to 2 by 3 r square minus y square whole power 3 by 2, and tau is equal to v a y bar by I n a b. V into 2 by 3 into r square minus y square whole power 3 by 2 by pi by 4 into r power 4 into 2 into root of r square minus y square. Tau is equal to 4v by 3 pi r power 4 into r square minus y square. Tau max or y is equal to 0 is equal to 4v by 3 pi r power 4 into r square is equal to 4 by 3 v by pi r square. Tau max by tau average is equal to 4 by 3. Now coming to another cross section, triangular cross section. B neutral axis will be d by 3 from bottom, and EF is like this, YE, and d by 2 shear stress variation, bending moment variation will be like this, so more here and less here. At position of shear stress, bending moment will 0 shear stress, bending moment will be maximum. Tau is equal to VA y bar by INA B is equal to V into half V into Y into 2D by 3 minus 2Y by 3 by BD cube by 36 into VY tau is equal to 12V by BD cube into DY minus Y square. For tau to tau max, d tau by dy is equal to 0. 12 by BD cube into D minus 2Y is equal to 0. Y is equal to D by 2. Tau max is equal to 3 by 2 into V by half BD. Tau Na is equal to 4 by 3 in tau max by tau average is equal to 3 by 2. Tau Na by tau Na is equal to 4 by 3 into V by half BD. Tau Na by tau average is equal to 4 by 3. At the location of maximum bending, shear stress must be 0, but at the location of maximum shear stress, bending stress need not be 0. Diamond cross section. Shear stress distribution will be like this: tau max, tau Na. Okay, if tau is equal to Va y bar by NAB is equal to V into half By into Y. Area half Vy into Y into d by 2 minus 2y by 3 by a power 4 by 12 into by. Tau is equal to 6v by a power 4 into dy by 2 minus 2y square by 3. For tau max, d tau by dy is equal to 0. 6v by a power 4 into d by 2 minus 4y by 3 is equal to 0. Y is equal to 3d by 8. Tau max is equal to 9 by 8 into v by a square. Tau max by tau average is equal to 9 by 8. Tau Na y is equal to d by 2 v by a square. Tau Na by tau average is equal to 1. Now summary of all above things: cross section, tau max by tau average, tau Na by tau average. For rectangle, tau max and tau Na are same, 3 by 2, 3 by 2. Circle, 4 by 3, 4 by 3, as here also same. But triangle, this is tau max by tau average is 3 by 2 and it is 4 by 3. Diamond, tau max by tau average is equal to 9 by 8. Tau Na by tau average is 1. I section. Find shear strain at the junction of web or flange. Flange side tau f is equal to va y bar by I capital B. Tau in web side, tau f is equal to va y bar by I small b. Tau w by tau f is equal to capital B by small b. This is inversely proportional to width anamata. Width. Okay. These are workbook question. Just same formula. Shear stress distribution for various cross sections. I section or hollow rectangle, cross circle, C section. The shear stress will be more where there is no material. Shear stress variation is like this, increasing parabolic, then also parabolic, but it is like this. Here also, as when there H or this thing, H or plus, when there is no material, there is more shear stress. Where there is less material, there is low shear stress. If there is more material, there is less shear stress. Here also same parabolic variation only. Here material is more, so less then material is less than more. Circular cross section is also like this, parabolic, then increases more, then less. Okay, chapter 7.